There is within all matter tiny particles called electrons, which are the tiny parts of atoms that orbit around the atom's centre. Along with these orbiting electrons, at the centre of atoms we have protons, which are of opposite types to electrons. Very strangely, this opposite typeness makes protons and electrons attract each other, but the same typeness makes objects repel. So two electrons, which are the same typeness, will repel each other, as do two protons, which are also of the same typeness. This attraction and repulsion force is called the Coulomb force. So between a proton and an electron, a force of attraction exists between them. Now, nobody really knows why this Coulomb force exists between particles causing attractions and repulsions, but we know that this force does exist, and its strength and behaviour has been measured very accurately and allows us to understand matter at a very detailed level. We can sum up this strange behaviour between particles to say that opposite types attract and similar types repel. Now let's say we have an atom that is missing an electron. This would mean this atom now has one extra proton more than it has electrons. So this unbalance of tightness we have given a name. So an atom that is in this state, we call it a positive ion. So here we have now introduced a new label. Instead of saying tightness, we've now introduced a label name called positive, which gives us the information that we have a missing electron in this atom. We also give a label name to electrons, which is called negative. This then is the concept of charge. It's simply unbalanced attractive and repulsive Coulomb forces. So when an atom or an object has a missing electron, we say that that atom or object has 1 unit of positive charge. So these are the reasons why we have the names positive and negative. It's to differentiate the typeness of objects so that we can say that they are attracted if they are of opposite type, or they are repelled if they are of the same type. So this is why we use the labels positive and negative, to give us that information in an easy form. When an atom or an object has an extra electron, we say that it is a negative ion with 1 unit of negative charge. This is where the idea of negative and positive charges came from. So from these ideas we can now begin to explain the concept of charge flow. Here is a thought experiment for you. Let's say we have some large collection of atoms, all with 1 missing electron each. Now of course they now all become positive ions, as we've just described, and they all repel each other because they are all of the same type. But from a nearby electron's point of view, all of these positive ions or atoms, Coulomb force of attractions, add up, and so the nearby electrons will feel this much stronger force of attraction. Now let's also say all of the electrons that were removed from these atoms in the process of making them positive ions in the first place are all being held inside some kind of container, and that all the positive ions that these electrons were removed from are held in another container. We can firstly imagine that pouring one container into the other will mean that the atoms will now get all of their electrons back, and we would then no longer have any positive ions, but instead a single container full of neutral atoms. So that's what we mean by the word neutral. But let's assume instead that we still keep the containers apart from each other. Now we can introduce a length of copper wire. We use copper because copper atoms have very loosely bound outer electrons. It means they're easy to dislodge. Now materials that are in this state, they're generally nearly always metals that lose outer electrons easily, are called good conductors. So these are the materials that we use for conductors. They are materials that have very loosely outer bound electrons. Now if we place our copper wire between these two containers, the attractive Coulomb force that exists will make the electrons leave its container and head towards the container of positive ions by moving through the copper wire. Now it's important to realise that the electrons that leave the container only fill the first few layers of copper atoms that are missing electrons along the first small section of the wire. Those first few layers of copper positive ions having lost their electrons due to a cumulative effect which starts almost the same time at other end of the wire, where last layer of electrons are attracted and move into the container that holds those positive copper ions. So what is this cumulative effect going on in the wire? Well, it's all to do with these attractive and repulsive forces acting along the whole length of the wire in almost instant time. Okay, let's use an analogy here to show you what I mean by that. Imagine a long queue of people, and the person at the far end of the queue is stood in front of a hard wall. Let's say we don't like him and we would like him to push into that wall without him knowing that you did it. How can you do that? Okay, I'm going to say this queue is very tight as everyone is squeezed against everyone else. Now to ensure that our victim hits the wall hard, all we have to do is push the last person in the queue forwards as hard and as quickly as we can. When we do that, this instigates a chain reaction along the queue with everyone pushing everyone else along the whole length of the queue until the man on the end gets pushed into the wall. Now the tighter and leaner the people in the queue are, the faster will this push impulse travel. Say we wanted this impulse to travel in almost instant time, and assuming we have superhuman strength, so we could arrange for that by pouring quick setting concrete on the whole queue, and that will produce the tightest queue imaginable. Now if we push this concrete queue, you know through common sense that that impulse will be almost instantaneous. So in the metal copper, the atoms are far more closely packed together than the atoms are in concrete even. So when we move an electron in or out of one end, the ripple effect of all the other electrons moving to fill the empty slot, like in our concrete queue, is almost instantaneous. It's faster in fact than our concrete queue. This happens because the Coulomb force of attraction and repulsion is incredibly strong. So in our wire, connected to the two containers, a layer of electron enters the wire due to the repulsive force they feel for each other. So to them the copper wire appears neutral, and so they can now get away from the container that holds all these electrons. As these electrons flow into the wire, the first few layers of copper atoms will lose their original electrons as the new ones push inwards. And at the other end we have the opposite situation, where the last layer of atoms in the copper will lose their outer electrons due to the attraction of the positive copper ions in the other container next to them. These copper atoms then in turn attract further electrons to fill the spaces, and this also ripples through the whole length of the copper in almost instant time, just like the concrete queue. So this is why our initial electrons moving out of our electron container only reach the first few layers. These layers will now hold the same number of electrons that were in our original container. With a finite number of electrons in our container, these will never get that far along the wire, but the effect of all the electrons that already exist in the copper wire, all moving from this impulse, will be, as our concrete queue example, an impulse almost at the speed of light. We can emulate this behaviour by charging a simple capacitor with a battery. Since once we have charged up our capacitor, we can think of each of the plates as our containers. One of the plates will consist of electrons or negative charge, whilst the other plate or container will hold an equal number of positive charges in the form of copper ions, copper atoms with missing electrons. The number of missing electrons will equal the number of electrons on the other plate. The Coulomb force of attraction holds them facing each other on the surfaces of the plates. This is the condition then of a charged capacitor. Now, just like in our last example, we can now join these two containers together with a length of copper wire. The same outcome will occur, so I'll now show you the nearest situation we can get to seeing charges move. In this simple circuit, when we join these containers or plates together, all the work that was done in separating out these charges, which was maybe done initially maybe many months ago when the 9-volt battery was charged up, will almost instantly be released. This work we refer to as energy, and the rate energy is released over time is called power. So a slow energy release is low power, and a fast energy release is high power. So we now will get a visual indication of charge movement and the power that is released as these charges move. Now, the capacitor plates were initially charged via the battery that took some time as we used a resistor to slow the charge flow rate. But now when I touch these wires, there is no more resistor involved here now. The wires themselves have hardly any resistance to the charge flow, so that will be much larger, and the energy will be released very quickly, almost instantly, as a short burst of high power. It's only a tiny amount of energy, but because it gets released so quickly, we get an interesting effect. Now, the Coulomb force of attraction was so strong that even before the two wires touched, the air molecules between the tiny gap between the two leads became ionized, and the separated charges moved through the ionized gas really quickly, with all the energy released at the same exact time. Hence a very short but large power spike, enough in fact to generate what is in effect a miniature lightning strike. This is then the closest we can get to seeing charge move, and an impressive visual indication of the power that exists in the Coulomb forces between charged objects.